Far beyond Neptune, a frozen world defies every rule we know. This is Quaoar, a dwarf planet hiding in the solar system's deep freeze, the Kuiper Belt. Discovered only in 2002, it was just another speck of light until astronomers looked closer. What they found has shattered expectations and rewritten chapters of planetary science. By the end of this journey, you will understand 25 profound mysteries that make Quaoar the solar system's greatest puzzle box. How can a ring exist where physics says it is impossible? Why is this ancient ball of ice far warmer than it should be? Each question pulls us deeper into the unknown. What does it mean when the universe keeps a secret this big, right in our own cosmic backyard? The first and most shocking secret of Quaoar was revealed in early 2023. Astronomers were studying the dwarf planet as it passed in front of a distant star, an event called a stellar occultation. As Quaoar's shadow raced across Earth, telescopes around the world watched for the star's light to blink out, but the light did something strange. It flickered not once but twice. A second, much fainter dip in starlight occurred both before and after Quaoar itself blocked the star. The data was unmistakable. Quaoar was not alone. It was surrounded by a ring, a thin, dense band of icy particles orbiting in perfect unison. This alone would be a remarkable find, as only a handful of small worlds in our solar system are known to have rings. But the real shock came when scientists calculated where this ring was located. It sits over 4,000 kilometers away from Quaoar's surface. That distance is the key to the mystery. In astrophysics, there is a critical boundary known as the Roche limit. Think of it as a celestial demolition line. Inside this zone, the gravitational tug from a large planet or dwarf planet is so fierce that it overpowers the forces holding smaller objects together. Any loose material, like ice and rock, gets shredded and cannot coalesce into a moon. Outside the Roche limit, that material is safe from being torn apart and can slowly clump together to form a satellite. All known planetary rings, like the magnificent ones around Saturn, exist inside their planet's Roche limit. They are debris fields, material that failed to become a moon. Quaoar's ring, however, laughs at this rule. It orbits far, far outside the calculated Roche limit for the dwarf planet. By all established physics, the particles in that ring should have felt safe. They should have felt the gentle nudge to come together, to attract one another, and over millions of years form a small, new moon of Quaoar, yet they did not. They remain suspended as a ring, a coherent band holding its shape in a region where rings are not supposed to survive. Observations from the European Space Agency's Cheops Space Telescope, designed to study exoplanets along with coordinated ground-based efforts, confirmed this impossible architecture. So we are left with the first great puzzle. What invisible force is at work out there in the dark? What is preventing these icy fragments from doing what gravity commands? The ring exists in a place of celestial peace, yet it refuses to build a new world. It is a structure that defies the very textbooks that explain how solar systems form. This is not just a ring, it is a question mark written in ice and dust orbiting silently in the void. The very existence of this impossible ring has sent planetary scientists back to their drawing boards, scrambling for an explanation. How can a structure so fragile survive in a gravitational environment that should have dismantled it long ago or encouraged it to coalesce into a moon? Several compelling yet unproven theories have emerged from the chaos. The first and most classic idea involves hidden guardians. In the elaborate rings of Saturn, tiny moons orbit just inside or outside the ring material, their gravity acting like celestial sheepdogs. These shepherd moons nudge stray particles back into line, maintaining sharp edges and preventing the ring from spreading out and dissipating. Could Quaoar have its own unseen shepherds? Small, dark moons, perhaps just a few kilometers across, might be orbiting within or near the ring. their subtle gravitational influence keeping the icy particles in a tight, stable band. Our telescopes simply haven't spotted them yet. Then there is the Moon we do know. Quaoar has one known satellite, a smaller world named Weywot. Its gravitational pull, even from a distance, could be creating resonances like rhythmic pushes on a swing that confine the ring particles to their specific orbit. This dance of gravity might set up a barrier, a zone where particles are trapped, unable to wander inward or outward to merge. But the most intriguing theory is also the most chaotic. It suggests the particles within the ring itself are not serene. Instead, they might be highly energetic, zipping around and colliding with each other at surprisingly high speeds. Think of it not as a calm disk of ice, but as a frenetic orbital bumper car arena. If these collisions are frequent and energetic enough, they could be preventing the gentle, sticky mergers needed to start building a moon. Every time two particles get close, a collision knocks them apart again, forever suspending the ring in a state of arrested development. This single mystery forces us to reconsider everything we thought we knew about rings. If Quaoar's ring can exist outside the Roche limit, then where else might we find these forbidden structures? Could other Kuiper Belt objects or even distant exoplanets host similar rings in gravitational peace zones? The textbooks on planetary formation now need a new chapter, one that admits some rings choose not to become moons, held in perfect, mysterious balance by forces we are only beginning to imagine. This defiance of gravity is not Quaoar's only surprise. Its very substance tells a stranger story. To understand a world, we must weigh it. Astronomers have measured Quaoar's mass by observing the graceful orbital dance of its moon, Weywot. They have also carefully calculated its size. By combining these two numbers, they arrive at a fundamental property, density. Density reveals what a world is made of. Is it a fluffy snowball, mostly ice, or a heavy ball of rock and metal? For objects in the distant Kuiper Belt, the expectation has always been the former. These are relics from the solar system's frozen attic, born in a region so cold that light gases like methane and water froze solid, becoming abundant building blocks. Most Kuiper Belt objects have densities consistent with this, resembling dirty snowballs or loose piles of icy rubble. Quaoar shatters that expectation. Its calculated density is remarkably high, nearly twice that of water. This number points to a composition that is startling. It suggests Quaoar is not a fluffy ice world. Instead, a significant portion of its mass, perhaps over half, must be made of dense rock and possibly even metal buried beneath its icy shell. This implies a massive, rocky core, a miniature planet hiding inside a frosty coat. The mystery is how such a dense object formed so far from the Sun. In the standard model of solar system formation, the inner regions were hot enough for rock and metal to condense, building the terrestrial planets like Earth and Mars. The outer regions beyond the frost line were cold enough for ices to dominate. The recipe for a Kuiper Belt object should be mostly ice with a sprinkling of rock. Quaoar's recipe appears reversed, a rocky planetesimal that somehow formed in the deep freeze or traveled an immense distance to get there. This dense core speaks of a violent and dynamic early Kuiper Belt. Perhaps Quaoar is not a primordial snowball but a cosmic collision survivor, the shattered remnant of a much larger, differentiated body that was torn apart, leaving its dense heart behind. Or maybe it formed closer to the Sun, in the rock-rich inner solar system, and was violently flung outward by the gravitational chaos of the giant planets in their youth, a refugee finding a new home in the icy darkness. Its high density is a silent testament to a past filled with cataclysmic impacts and gravitational slingshots, a history written not on its surface but deep within its heavy heart. The dense, rocky heart of Quaoar is cloaked by a surface that holds its own vivid secret. From afar, this dwarf planet appears as a mottled mix of grays and whites, typical for an icy body. But detailed observations reveal a startling anomaly, a large, distinctly red patch staining its otherwise pale face. This is not a subtle tint, but a bold, localized stain, a mysterious blemish on the frosty world. The color red, in the cold chemistry of the outer solar system, is a telltale signature. Spectrometers, which break down light to reveal chemical fingerprints, point to the presence of complex organic molecules called tholins. Tholins are not alive, but they are the building blocks of life, intricate carbon-rich compounds forged when simple ices like methane and nitrogen are bombarded by radiation, whether from the sun or cosmic rays. It is a process like cosmic cooking, where ultraviolet light and charged particles bake basic ingredients into a complex reddish-brown tar. This substance paints vast areas of other distant worlds, like Pluto and Saturn's moon Titan, giving them their characteristic rusty hues. On Quaoar, however, the stain is not global. It is concentrated, a single prominent feature that demands an explanation. Why is this ruddy color so focused in one area? One compelling theory points to violence from above. The red spot could be the scar of a geologically recent impact. A comet or another Kuiper Belt object may have slammed into Quaoar, punching through the bright surface ice and excavating material from below. This excavated material could be richer in the organic compounds that readily turn into tholins when exposed to space, creating a fresh, dark stain on the point of impact. Alternatively, the violence may have come from within. Quaoar could possess cryovolcanoes, not erupting with molten rock, but with a frigid slurry of water, ammonia, or methane. A powerful eruption might have spewed this subsurface slush across the landscape. As that plume settled, the volatile chemicals within it would have been irradiated by sunlight, rapidly cooking into the reddish tholin deposit we see, painting the area around the volcanic vent. The most intriguing possibility is that the spot is a permanent window. It might be a region where the thin, bright veneer of surface ice has been stripped away, either by impact, erosion, or geological activity, permanently exposing a deeper layer that is inherently different in composition. This would mean Quaoar is not a uniform ball, but a layered, two-toned world with a hidden subsurface stratum rich in the precursors to tholins. This single spot of color transforms Quaoar from a monochrome ice ball into a world with a geological history, a canvas showing evidence of either a catastrophic event, an internal upheaval, or a fundamentally patchwork construction. That red stain is a message written in the complex language of organic chemistry, waiting for us to decipher its origin story. That vivid red stain hints at a surface scarred by violence, but to find the true architect of chaos, we must look beyond Quaoar itself to its lone known companion. Orbiting the dwarf planet is its moon, Weywot, a smaller world named for a Tongva creator deity. Yet Weywot's path is anything but divine and orderly. Its orbit is profoundly strange, tilted at a severe angle relative to Quaoar's own equator. Imagine a planet with a moon that does not circle around its waistline, like our moon does around Earth, but instead loops dramatically over its poles and under its belly in a wild, inclined dance. This is not a placid, co-formed satellite settled into a calm, equatorial plane. This is the signature of a violent past written in celestial motion. Such a wildly tilted orbit is a glaring clue. In a calm, orderly system, moons typically form from a flat disk of debris swirling around a planet's equator, eventually coalescing into satellites that orbit neatly in that same plane. A moon flung into a high-inclination orbit is a moon that has been profoundly disturbed, a clear signpost pointing to a moment of catastrophic upheaval. The leading theory is a giant impact. In the solar system's violent youth, a colossal object, perhaps another sizable Kuiper Belt body, could have slammed into a young, still-forming Quaoar. This apocalyptic collision would have vaporized ice and shattered rock, blasting a tremendous cloud of debris into space around the wounded dwarf planet. From that chaotic, swirling cloud, Weywot could have coalesced, but the incredible energy of the impact would have given the forming moon a tremendous kick, launching it into the erratic, tilted orbit we see today. The alternative is a gravitational thriller. Perhaps Weywot formed in a calm, equatorial orbit, but its peace was shattered later. Another moon, now lost, might have once shared Quaoar's sky. The gravitational tug-of-war between these two satellites could have gradually, over eons, pumped energy into Weywot's orbit, pushing and pulling it into its current steeply inclined path. The other moon, destabilized, might have eventually crashed into Quaoar or been flung entirely out of the system, leaving Weywot as the sole survivor of this ancient celestial duel. Either scenario paints a picture of a far more dynamic and dangerous early Kuiper Belt than we once imagined. Weywot's odd orbit is more than an orbital curiosity, it is a forensic record. By studying its precise tilt and shape, astronomers can run the cosmic clock backward, simulating gravitational interactions to uncover what cataclysm set this moon on its peculiar course. That tilted path is a permanent monument to the moment Quaoar's history was violently rewritten, a silent witness to the chaos from which this frozen world emerged. The violence that shaped Weywot's orbit may have left a deeper, more profound legacy within Quaoar itself, a hidden warmth in the eternal freeze. For a world orbiting nearly 44 times farther from the Sun than Earth, Quaoar should be profoundly, deathly cold. Simple models predict its surface temperature should hover just a few dozen degrees above absolute zero, a place where the very air we breathe would freeze solid in an instant. Yet observations tell a different story. Thermal measurements indicate Quaoar is noticeably warmer than it has any right to be. This temperature anomaly is a quiet but significant clue that something is generating heat deep within this frozen sphere. The first suspect is the dwarf planet's own dense, rocky heart. If Quaoar possesses a substantial core rich in elements like uranium, thorium, and potassium, the slow, relentless decay of these radioactive atoms could be providing a steady trickle of heat, a natural nuclear furnace buried for billions of years. This process, called radiogenic heating, warms the interior of Earth and is likely at work within Quaoar, preventing its deep interior from becoming a completely uniform block of ice. But there is another, more dynamic source to consider. The gravitational tug-of-war between Quaoar and its moon, Weywot, might be doing more than just tilting orbits. As Weywot travels its elongated, inclined path, its gravitational pull on Quaoar changes constantly, stretching and flexing the dwarf planet's interior. This continual kneading, known as tidal heating, generates friction and warmth. It is the same process that keeps the interiors of moons like Jupiter's Io and Europa molten and active. For a small world like Quaoar, even a modest amount of tidal heating could be significant, potentially maintaining a slushy, malleable layer between the icy crust and the rocky core. This leads to the most thrilling possibility hinted at by the extra warmth, a subsurface ocean. If internal heat from radioactivity and tidal forces is sufficient, it could melt a layer of water ice deep beneath the surface, creating a vast, dark, liquid sea encased in a global shell of solid ice. Such oceans are now suspected to exist on several distant moons like Europa and Enceladus, and are considered prime targets in the search for extraterrestrial life. Could Quaoar, this small, dark world in the Kuiper Belt, also harbor a secret ocean? The warmth we detect is a whisper, a suggestion that its story is not one of frozen geologic death, but of hidden dynamic possibility. This thermal mystery forces us to ask what other active processes might be at work in the solar system's forgotten frontier, where even ancient worlds may hold pockets of warmth and perhaps, against all odds, liquid water. That hidden warmth and potential for a subsurface ocean raises a profound question about the world above. If there is heat below, and we know volatile ices like methane and nitrogen frost its surface, then where is the air? For a world of Quaoar's size, an atmosphere was almost an expectation. We have seen it on smaller, colder bodies. Pluto, though larger, maintains a tenuous but detectable shroud of nitrogen and methane. Even some asteroids outgas sporadically, yet when astronomers point their most sensitive instruments at Quaoar, they find no evidence of a surrounding gaseous envelope. The atmosphere, it seems, is missing. This absence is a glaring puzzle. The logic was straightforward. Quaoar is large enough for its gravity to hold onto light gases, and its surface contains the very ices that, when warmed even slightly by the distant sun, should sublimate, turning directly from solid to gas. This process should create a seasonal atmosphere, a thin veil that freezes back onto the surface as the dwarf planet moves farther along its elongated orbit. But the data shows nothing. This forces scientists to consider several unsettling possibilities. The first is a story of permanent loss. Perhaps Quaoar did have a more substantial atmosphere in its distant past, but over billions of years it has bled away into space. Impacts could have stripped it, or the gentle but relentless pressure of solar wind, even this far out, could have slowly eroded it molecule by molecule, leaving the surface ices bare and exposed. The second, more dynamic idea is that we are simply looking at the wrong time. Quaoar's orbit is not a perfect circle. Its distance from the Sun varies. It is possible that its atmosphere is not missing but sleeping. During its closest approach to the Sun, a brief summer might occur where surface ice is warm enough to create a temporary, ultra-thin haze. By the time we observed it, it may have already collapsed, freezing back onto the surface in a global, silent frostfall. We may have caught Quaoar in its deep winter, with every volatile molecule locked in rigid ice. But the third possibility is the most intriguing and speaks to the strange nature of its surface. The methane and nitrogen we detect might not be free to sublimate at all. They could be trapped. Imagine these volatile ices not as a loose frost, but as prisoners within a much harder, more stable matrix of water ice. Think of it like a sponge made of rock-hard water ice with the softer methane trapped in its microscopic pores. Or through eons of radiation processing, the surface ices may have been transformed into a rigid, porous crust, a kind of cosmic insulation that prevents the volatiles underneath from ever escaping. The ices are there, but they are entombed, unable to become gas. This missing atmosphere is a silent clue to Quaoar's true nature. It suggests a surface that is geologically dead and stable on a grand scale, or one whose activity is so subtle and locked away that it cannot muster even a wisp of gas. It tells us that the presence of volatile ingredients is not enough. You need the right conditions, the right heat, and the right kind of surface to set the air free. Quaoar, it seems, holds its breath permanently, keeping its secrets locked in ice. The silent, frozen surface of Quaoar may hold a clue to its relationship with its erratic moon, a connection written not in words but in rotation. This is the mystery of tidal locking, a cosmic dance that could bind these two worlds in a perpetual gravitational embrace. Many moons in our solar system, including our own, are tidally locked to their planets. This means they rotate on their axis in exactly the same time it takes to complete one orbit, forever showing the same face to their parent world, like a dancer who always keeps their partner in view. The question is, has Quaoar done the same for Weywot? Is the dwarf planet's rotation perfectly synchronized with its moon's long, tilted orbit, so that one hemisphere of Quaoar constantly stares at Weywot while the other looks eternally away? The evidence is currently ambiguous, a puzzle without a clear solution. On one hand, the mechanics seem to favor it. Tidal locking is a gradual process. Over millions or billions of years, the gravitational pull of a moon creates a slight, persistent bulge on its planet. As the planet rotates, this bulge is tugged slightly ahead, and that gravitational interaction acts as a brake, slowly sapping the planet's spin until its rotation matches the moon's orbital period. For a system as old as Quaoar's, with a moon as substantial as Weywot, there has been ample time for this slow, cosmic breaking to reach its conclusion. If Quaoar is locked, it would be a testament to the relentless, smoothing power of gravity, even in the solar system's quietest neighborhood. Yet there is a compelling reason to doubt it. Weywot's orbit is not just tilted, it is also notably elliptical or oval-shaped. This means the moon's distance from Quaoar changes significantly throughout its journey. For a perfect, stable tidal lock to occur, a more circular orbit is usually required. The varying gravitational tug from an elliptical moon can create a complex, wobbling interaction that might prevent a clean, synchronous lock from ever fully settling in. It could leave Quaoar in a state of spin-orbit resonance, rotating perhaps 3 times for every 2 of Weywot's orbits, a more complex rhythm in their distant dance. Why does this technical detail matter so profoundly? The answer lies in the story it tells about time and structure. If Quaoar is tidally locked with Weywot, it forces us to recalculate the clockwork of the Kuiper Belt. Achieving lock requires specific conditions, including internal flexibility. It suggests Quaoar's interior is or was malleable enough to form that responsive tidal bulge, possibly pointing to a subsurface ocean or a generally soft, deformable structure that allowed the locking process to proceed efficiently. A lock would imply a system that settled into its current state long ago, a quiet, mature partnership. If Quaoar is not locked, the implications are even more stirring. It means something is actively preventing that final gravitational synchronization. Perhaps the system is still dynamically young, reverberating from the giant impact that formed Weywot and hasn't had time to settle. Maybe Quaoar's interior is too rigid, too cold and unyielding to form the necessary tidal bulge, hinting at a solid, frozen through composition with no hidden ocean to allow flex. Or the chaotic influence of other, unseen bodies could be perpetually disturbing the dance. Determining the state of this lock is like finding a single page from Quaoar's diary. It reveals whether this world is geologically supple or rigid, whether its history with its moon is one of settled harmony or ongoing, unbalanced tension. It is a simple yes or no question about rotation that unpacks the very nature of the dwarf planet's heart and the turbulent story of its sky. The question of Quaoar's locked rotation leads us to an even more fundamental mystery about its very identity. Is Quaoar a single world or is it two? This is the binary object debate, a question that challenges our most basic picture of this distant dwarf planet. Some astronomers scrutinizing its light curve, the subtle pattern of brightness changes as it spins, have noted complexities that a simple, lumpy sphere cannot easily explain. The variations are not perfectly smooth or regular. This has led to a radical proposal that what we call Quaoar might actually be 2 similarly sized bodies locked in an incredibly tight mutual orbit, forever dancing around a shared point in space. Imagine 2 frozen worlds, each hundreds of kilometers across, so close they nearly touch, whirling around each other every few hours like a colossal, icy dumbbell spinning in the void. This binary nature would elegantly solve several puzzles. It could account for oddities in its calculated shape and even its unusually high density, as the gravitational interplay between 2 dense cores could skew our measurements from afar. If true, Quaoar would join a small club of known binary Kuiper Belt objects, revealing a fascinating mode of formation where 2 partners found each other in the early solar system and never let go. Yet this elegant solution would instantly create far more profound and dizzying problems. It would make the entire system we have described so far, the ring and the moon Weywot, an architectural nightmare. The gravitational environment around a tight binary is not the clean, central pull of a single world. It is a chaotic, shifting field of competing tugs from 2 moving masses. For Weywot to maintain its stable, though tilted, orbit around such a chaotic double anchor would require an orbital ballet of incomprehensible precision. And the ring, that delicate band of particles existing in its impossible zone, its survival becomes an even greater miracle. The particles would be subjected to a wildly variable gravitational force, constantly jerked and stirred by the binary's waltz, making their coherent, circular band seem almost nonsensical. So we are left with a profound either-or. Either Quaoar is a single, albeit very strange, world with a dense core and a perplexing ring, or it is a binary pair whose existence makes the ring and the moon seem like gravitational impossibilities. Both answers are deeply unsettling. Both force us to rewrite our models. The light curve holds the secret, a faint, rhythmic signal blinking across 4 billion miles, waiting for us to finally decode whether we are looking at one mystery or two. Those rhythmic pulses of light hold more than just a binary secret. The precise measurement of Quaoar's brightness over time, its light curve, reveals a pattern of irregularities that refuses to settle into a simple explanation. As the dwarf planet rotates, bringing different faces into view, astronomers expect a smooth, predictable rise and fall in reflected sunlight. Instead, they see dips and spikes that are too sharp, too sudden, to be explained by the gentle spin of a frozen world or the predictable eclipse of its moon, Weywot. These are not the shadows of known companions, but flickers of something else entirely, brief winks in the constant starlight that suggest Quaoar's environment is far from static. One compelling possibility lies on its surface. These irregularities could be caused by stark contrasts in albedo, the scientific term for reflectivity. Imagine Quaoar not as a uniformly gray ball of ice, but as a world with a dramatically patchwork complexion. Vast, dark plains of ancient, radiation-processed tholins could lie adjacent to brilliant, fresh ice fields exposed by a recent impact or geological shift. As this mottled surface turns, the amount of sunlight bouncing back to our telescopes would change abruptly, not smoothly. A sharp dip in brightness could mean a large, dark feature, like that mysterious red stain, has rotated into view. A sudden spike might reveal a pristine, reflective ice patch catching the sun. This would paint Quaoar as a geologically complex world, its face a record of impacts, eruptions, and weathering written in stark black and white. But there is a more ephemeral explanation. Could these light variations be the ghost of an atmosphere? While no permanent gas envelope exists, Quaoar might experience fleeting outbursts. Seasonal warming or heat from a cryovolcanic vent deep below could trigger a temporary sublimation of surface ices. A localized cloud of nitrogen or methane haze, thin and transient, might puff into existence, scattering sunlight and subtly dimming the world's glow for a short time before freezing back onto the surface as frost. These unpredictable hazes would create irregular, short-lived dips in the light curve, evidence of a world that occasionally, quietly exhales. The most unsettling possibility involves unseen traffic in Quaoar's skies. The irregular dips could be caused by other, smaller bodies orbiting the dwarf planet. Not a moon as large as Weywot, but a swarm of tiny, dark moonlets or a dense arc of debris within or near the main ring. As these fragments pass between Quaoar and our telescopes, they would cast minuscule shadows, creating brief, jagged fluctuations in the light we receive. This would imply Quaoar's orbital space is cluttered and dynamic, a busy crossroads where collisions and gravitational captures are ongoing processes. Each flicker in the data is a signal without a clear source, a clue pointing to activity we cannot yet see. It tells us that Quaoar is not a dead, finished sculpture. Its story is still being written, whether by the slow painting of its surface, the faint breath of temporary hazes, or the silent motion of hidden companions. The irregular light curve is a heartbeat monitor on a world 4 billion miles away, and its rhythm is arrhythmic, unpredictable, and alive with mystery. Methane ice glitters coldly on Quaoar's surface, a volatile substance that should have vanished long ago. Its presence is a clue, a chemical fingerprint pointing back to the dwarf planet's origin, and perhaps to processes still unfolding within. Where did this methane come from? The simplest answer is that it is primordial, a fossil from the birth of the solar system itself. In the frigid outer reaches of the original solar nebula, methane molecules could have frozen directly onto dust grains, becoming a fundamental building block for worlds like Quaoar. If this is the case, then the methane we see is a cosmic relic, preserved in a deep freeze for over 4 billion years, untouched and unchanged since the dawn of our planetary family. It would make Quaoar a pristine time capsule, holding a sample of the ancient ingredients from which the outer solar system was built. A more violent origin story involves delivery from space. The Kuiper Belt is a shooting gallery of icy remnants. Comets and smaller bodies rich in methane ice could have bombarded Quaoar throughout its history. Each impact would have been a miniature seeding event, splashing methane across the surface and mixing it with native ices. In this scenario, the methane is not Quaoar's original material, but a later addition, a layer of cosmic paint applied by countless collisions. This would mean the surface we see is a palimpsest, a record of everything that has ever crashed into this distant world. Yet there is a third, far more speculative possibility that sends a thrill through the scientific imagination. Could the methane be generated from within? On Earth, vast amounts of methane are produced biologically by microbes in places like wetlands and the digestive systems of animals. While invoking life on a frozen dwarf planet is an enormous leap, the chemistry itself is not exclusive to biology. Geological processes known as serpentinization can produce methane abiotically. This occurs when water reacts with certain kinds of rock, like olivine, in a process that releases hydrogen, which can then combine with carbon to form methane. If Quaoar possesses a rocky core and a subsurface ocean warmed by radioactivity or tidal forces, these exact chemical reactions could be occurring right now in the dark under immense pressure. A hidden water rock interface deep below the ice could be a factory, steadily producing methane that slowly percolates upward, eventually reaching the surface to replenish the ices we detect. This would transform Quaoar from a static relic into a geochemically active world, with an internal engine quietly manufacturing the very compounds that frost its face. The source of the methane ice is more than an academic puzzle. If it is primordial, Quaoar becomes a museum of solar system infancy. If it is delivered, it is a testament to a violent, chaotic past. But if it is being made, if that methane is the product of ongoing geochemistry in a hidden ocean, then everything changes. It would be indirect evidence for that warm, wet, rocky interface that astrobiologists dream of, an environment where, against all odds, the basic prerequisites for life might one day have arisen. The glittering methane is a message, and we are only beginning to translate its ancient or perhaps ongoing story. The methane on its surface whispers of ancient origins, but Quaoar's path through space tells a story of its own. While most of its neighbors in the Kuiper Belt follow wildly tilted and inclined orbits, Quaoar's own journey is remarkably orderly. Its orbital plane is aligned almost perfectly with the solar system's ecliptic, that flat disk where the planets themselves orbit the sun. This is not a small detail. It is a profound clue about where and how this world was born. The Kuiper Belt is a chaotic realm, a leftover construction zone filled with icy debris. Over billions of years, the immense gravity of Neptune has acted like a cosmic sculptor, nudging and tossing many of these objects into orbits that are sharply inclined, like leaves scattered by a strong wind. Finding a large object like Quaoar that still orbits so neatly in the primeval plane is like finding a single, undisturbed brick in the middle of a demolished building site. So what does this pristine alignment mean? One possibility is that Quaoar is a true primordial relic, a fossil from the very first days of the solar system. It may have formed right where it sits today, in the cold outer disk, and was miraculously spared from the gravitational bullying that knocked its neighbors askew. Its orbit remained clean and undisturbed, a silent witness to the chaos that reshaped the rest of the Kuiper Belt. This would make Quaoar one of the most original, untouched pieces of our solar system's history, a time capsule that never felt the push of a giant planet's hand. But there is another, more dramatic interpretation. This orderly orbit might be a mark of exile. Perhaps Quaoar did not form in the deep freeze at all. It could have been assembled much closer to the Sun, in the region of the giant planets, where orbits naturally align with the ecliptic. Then, during the solar system's violent youth, a gravitational encounter with Jupiter or Saturn could have acted like a cosmic slingshot, hurling Quaoar outward on a fast, chaotic journey. Yet, by a strange twist of celestial mechanics, that violent ejection could have deposited it into a stable, circular orbit that just happens to line up neatly with the planetary plane. In this story, its alignment is not a sign of peace, but a scar from a traumatic expulsion. It is a refugee whose path betrays its inner solar system origins. This single characteristic, the flatness of its orbit, forces us to choose between two radically different biographies. Is Quaoar a local, a homegrown Kuiper Belt object that lived a quiet life? Or is it an immigrant, a rocky interloper from the warmer inner realms, now wearing a cloak of ice in a foreign land? Its orbit is a line on a celestial map, and it points in two completely opposite directions, each leading to a different chapter in the epic tale of our solar system's violent birth. Its orderly orbit hints at a calm history, but the very shape of Quaoar tells a conflicting, more turbulent tale. This is the oblateness enigma, where the most basic measurement of a world, its figure, refuses to give a straight answer. From some angles, the data suggests Quaoar is satisfyingly round, a near-perfect sphere as its gravity would dictate for an object of its size. A world that has relaxed into hydrostatic equilibrium, the state where its own weight has smoothed it into the most efficient shape possible. Yet other observations introduce a tantalizing wrinkle. They point to a slight flattening, an oblateness, as if Quaoar is subtly squashed at its poles and bulging at its equator. This is the shape of a world spinning with purpose, where centrifugal force fights against gravity's pull to create a slightly flattened sphere. The degree of that flattening is a direct window into the world's interior. A very oblate shape suggests a fast spin and a relatively soft, malleable interior that can flow and deform in response. A perfect sphere suggests either a very slow rotation or an interior that has become cold, rigid, and unyielding, frozen solid into a permanent spherical form. But the data is ambiguous, caught between these two states. This conflict forces us to ask fundamental questions about what lies beneath the ice. If Quaoar is spinning fast enough to be oblate, what does that say about its core? A dense, rocky core would resist deformation, fighting against the flattening. A more uniform mixture of ice and rock, or a global subsurface ocean, would allow the world to flex more easily into that oblate shape. The very attempt to measure its figure becomes a diagnostic tool for its hidden layers. Yet there is a third, more dramatic possibility hinted at by irregularities in the light curve. Perhaps Quaoar is not a smooth, oblate spheroid at all, but retains an irregular, lumpy shape like a potato. This would be a bombshell revelation. For an object of Quaoar's mass, gravity should have erased such primordial lumps billions of years ago unless something stopped the process. An irregular shape would scream of a recent catastrophic trauma. A colossal impact could have shattered its symmetry, leaving it misshapen, with gravity still too weak or the interior too cold and rigid to pull it back into a sphere. It would mean we are looking at a world that is geologically dead, frozen in a moment of violence, unable to heal its own wounds. Or it could mean its composition is unexpectedly strong, a rocky rubble pile held together by its own mass but never becoming warm or soft enough to fully relax. Pinpointing its true shape is not an academic exercise. It is the key that locks together the mysteries of its rotation, its density, and its thermal history. Is Quaoar a soft, warm, and active world still settling into its form, or a cold, rigid fossil preserving the scars of an ancient cataclysm? Every curve of its silhouette holds the answer. That ambiguous shape caught between sphere and splat hints at an interior that might still be soft and warm. Could that hidden warmth ever break through? The search for cryovolcanic features on Quaoar is a hunt for the ultimate proof of life within this frozen world. Cryovolcanoes are not fire mountains but ice volcanoes. Instead of erupting molten rock, they spew a frigid slurry of water, ammonia, methane, or other volatile compounds, a thick, icy lava that oozes across the landscape before freezing solid. On moons like Neptune's Triton or Saturn's Enceladus, these features have rewritten our understanding of geological activity in the solar system's cold reaches. For Quaoar, the evidence is tantalizingly indirect, glimpsed only in the blurry pixels of our most powerful telescopic images. Astronomers scrutinizing its faint, distant disk have noted certain geological formations that resist easy explanation. There are broad, smooth plains that seem unusually level, as if resurfaced by a fluid that later froze. Other areas show subtle, dome-like bulges, possible cryovolcanic domes where viscous icy magma pushed up from below but never fully erupted, creating a frozen blister on the surface. Perhaps most intriguing are long, faint albedo streaks, potential flow features where a cryolava might have trickled from a vent, leaving a dark or bright stain across the older terrain. These are not crisp photographs, but statistical hints and topographic suggestions, the ghostly impressions of activity painted in low-resolution light. The driving force behind such eruptions would be the same internal heat that warms Quaoar beyond expectation, a subsurface ocean kept liquid by radioactive decay in the core and needed by Weywot's tidal pulls provides the reservoir. If the icy crust above that ocean fractures, perhaps from the stress of tidal flexing or the pressure of the liquid below, the mixture could be forced upward. It would erupt not with fire and smoke, but in a silent, slow-motion geyser of supercooled slush, painting the landscape with fresh, bright ice or complex, dark organics. The discovery of an active cryovolcano on Quaoar would be a revolution. It would shatter the image of the Kuiper Belt as a graveyard of dead, static ice balls. Instead, Quaoar would join an elite club of active icy worlds, proving that geological vitality is not confined to the warm embrace of giant planets. It would confirm the existence of that subsurface ocean in the most dramatic way possible, not through indirect thermal readings, but by showing us its contents spilled across the surface. This would make Quaoar a prime candidate in the search for habitable environments, as cryovolcanism provides a direct mechanism for cycling chemicals between a warm, wet interior and the surface, creating the kind of complex chemical soup that could potentially spark probiotic chemistry. The silent, dark plains we see might not be ancient tombs, but frozen pages from an ongoing geological diary, waiting for a closer look to read their explosive history. Quaoar's solitary orbit may be a clue to its violent origins, a single piece of a much larger, shattered puzzle. To understand where it truly belongs, we must zoom out and see it within its crowded neighborhood, the Kuiper Belt. This vast region is not a uniform swarm of ice. Astronomers classify its inhabitants into distinct populations, each telling a different story of solar system history. There are the classical Kuiper Belt objects orbiting in relatively calm, near-circular paths, the local residents who have lived there peacefully for eons. And then there are the scattered disk objects, the wild ones. These are bodies with highly elongated, tilted orbits, evidence that they were violently scattered outward by Neptune's gravity in the solar system's chaotic youth. Quaoar, with its remarkably flat and orderly orbit, fits neatly into neither category perfectly. It is too well behaved to be a scattered disk refugee, yet its exact orbital parameters make it a slight outsider among the classical population as well. This classification headache leads to a deeper forensic question: is Quaoar part of a collisional family? Across the solar system, from the asteroid belt to the Kuiper Belt, we find families of objects. These are groups of asteroids or icy bodies that share strikingly similar orbits and often similar compositions. They are not random neighbors, they are siblings. They are the shattered pieces of a single, larger parent body that was destroyed in a cataclysmic impact billions of years ago. The fragments from that explosion, traveling at similar speeds, end up orbiting the Sun together, a permanent monument to a past catastrophe. Finding such a family for Quaoar would be a revelation. It would mean Quaoar itself is not a primordial world, but one of the largest surviving chunks of a much more massive ancient planetesimal that was blown apart. Its moon, Weywot, could then be understood not as a product of a single, isolated impact on Quaoar, but as another fragment from that same primordial breakup, a sibling that was captured into orbit. The entire system, the dense core, the tilted moon, even the strange ring, could all be explained as debris from this one apocalyptic event. The hunt, however, has so far come up empty. Detailed surveys of the Kuiper Belt have mapped the orbits of thousands of objects, searching for clusters that match Quaoar's path. While some potential, very distant relatives have been suggested, no clear, definitive family has been identified. Quaoar's specific orbital fingerprint, its particular combination of distance, tilt, and shape, makes it an outlier. It sits alone. This solitude is profoundly telling. It means one of two things. Either the giant impact that likely formed Weywot was so unique and violent that it completely dispersed all the other debris, ejecting it on wildly different trajectories, leaving no trace of a family behind. Or Quaoar's journey has been so isolated and undisturbed that it never experienced that kind of shattering collision at all, and its moon Weywot is the product of a far more localized, gentler event. Its lack of a family is a silence that speaks volumes. It suggests that the history of the Kuiper Belt is not just one of simple smashing and scattering, but a complex tapestry of quiet survivors and lone wolves, of impacts that create families and impacts that leave only orphans. Quaoar, it seems, might be one of those orphans, a world whose story of formation was so uniquely violent or so strangely peaceful that it left no other witnesses in its orbital path. The light bouncing off Quaoar's frozen surface carries a chemical confession, but when scientists break it down, the story refuses to be simple. Using powerful infrared telescopes, astronomers have analyzed the spectrum of sunlight reflected from the dwarf planet, looking for the unique absorption lines that act as fingerprints for different ices and minerals. What they found is deeply puzzling. While there are clear signs of water ice, methane, and possibly ammonia, there are also distinct, unidentified signatures. These are absorption lines that do not match any known substance in our planetary science databases perfectly. It is as if Quaoar's surface is coated in a substance we have never catalogued, a chemical mystery written in infrared light. These spectral ghosts are direct evidence that the surface chemistry of this distant world is far more complex than a simple mixture of common ices. One compelling possibility is the presence of highly complex, radiation-processed organics. We know tholins create a reddish color, but the specific molecular structures formed by eons of cosmic irradiation could be incredibly intricate, creating unique spectral bands we have not yet recreated in laboratories. Quaoar's particular blend of surface ices, bombarded by a specific history of solar and cosmic radiation in its unique orbit, may have cooked up a one-of-a-kind organic tar with its own infrared signature. Another exotic candidate involves the very structure of the water ice itself. Water ice is not always the same. Under different temperature and pressure conditions, it can form various crystalline phases, each with a slightly different arrangement of molecules and therefore a different spectral fingerprint. The ice on Quaoar's surface, subjected to temperatures near absolute zero for billions of years, might have settled into a rare, metastable crystalline form that we rarely see on Earth or even on closer, warmer, icy moons. This would be a direct record of the profound and unending cold, or perhaps the answer lies in chemistry driven by its hidden ocean. If a subsurface sea exists, it is not pure water. It would be a brine rich in dissolved salts like ammonia, sodium chloride, or magnesium sulfate. If cryovolcanism has ever brought that brine to the surface, the rapid freezing and subsequent irradiation could create exotic hydrated salts or mineral complexes with entirely new spectral features. These would be minerals born not of volcanic fire but of cryovolcanic cold, their signatures a testament to a hidden, liquid history. Each unidentified line in the spectrum is a question. They force us to admit that our understanding of chemistry in the outer solar system is incomplete. Quaoar is not just a museum of primordial ices. It is an active laboratory where extreme cold and relentless radiation are constantly inventing new materials. Decoding these spectral whispers is the only way to read the full recipe of this frozen world, a recipe that may include ingredients we have never before imagined. These conflicting chemical signatures paint a surface with a split personality, a duality that echoes in its very skin. Quaoar presents us with a profound age paradox, a timeline that seems to contradict itself. On one hand, its face is ancient. Planetary scientists use craters as clocks, counting the pockmarks left by eons of impacts to estimate a world's age. The more densely cratered a surface, the older it is, as it has had more time to accumulate scars. From what we can discern, Quaoar's surface appears heavily cratered, a battered landscape that suggests it has looked up at the same dark sky for billions of years, quietly collecting the bruises of a violent neighborhood. This is the face of a primordial relic, a fossil from the solar system's dawn that has remained geologically dead and unchanged. Yet, whispering against this narrative are signs of youth and activity. The impossible ring itself is a structure of astonishing delicacy. In the dynamic environment of the Kuiper Belt, such a thin, dense band of particles should not survive for the age of the solar system. Collisions with micrometeoroids, the subtle pressure of solar radiation, and gravitational perturbations should have either dispersed it or caused it to clump into a moon long ago. Its very existence hints that it might be a far more recent feature, perhaps only a few 100 million years old or even younger. Furthermore, the possibility of cryovolcanic resurfacing and those puzzling spectral signatures suggest that the surface is not a static monument. Some process, whether internal heat or chemical evolution, appears to be actively repainting parts of this ancient canvas. So how can one world be both an ancient fossil and a geologically active youth? The answer lies in the concept of a dual personality, a world where time flows at different speeds in different layers. Imagine Quaoar as an old, weathered book. Its cover, the heavily cratered crust, is worn and ancient, its pages written over 4 billion years ago. But hidden within that book are inserts, fresh pages added much later. A cryovolcanic eruption is like an author adding a new, crisp chapter, covering an old, cratered plain with a smooth sheet of fresh ice, effectively resetting the crater clock in that one localized area. The ring could be like a bookmark, a recent and fragile addition placed within the ancient tome. This means Quaoar is not simply old or young, it is a palimpsest. It is a cumulative record where the deepest layers tell the story of catastrophic formation and early bombardment, while the surface occasionally receives edits from a still beating internal heart. The ancient crust testifies to a quiet, cold existence for most of its life, while the ring and potential resurfacing events are brief, brilliant flashes of activity, moments where the dwarf planet briefly woke up, changed its face, and then returned to its frozen slumber. This paradox forces us to see time not as a single line, but as a series of overlapping narratives. Quaoar holds the entire history of the outer solar system, from its violent birth to occasional, mysterious pulses of renewal, all frozen in layers of ice and etched upon its singular, contradictory surface. Quaoar's solitary and orderly path may hold a clue not just to its own past, but to the fate of our entire solar system. This brings us to one of the most speculative and thrilling mysteries, the potential gravitational handshake between this known dwarf planet and a world that remains purely theoretical, the elusive Planet 9. For years, astronomers have noticed a strange pattern in the distant solar system. Several extreme trans-Neptunian objects, those icy bodies with orbits far beyond Neptune, share a peculiar orbital alignment. Their elongated paths seem to be clustered as if something massive, something with 10 times the mass of Earth, is herding them through the dark. That something is the hypothesized Planet 9, a giant world lurking perhaps 20 times farther from the Sun than Neptune, on a monstrous orbit that takes thousands of years to complete. The question now is, does Quaoar's own orbit show any fingerprints of this phantom giant's influence? The analysis is subtle and hotly debated. Quaoar's orbit is not as extreme as those of the prime suspects used to define the Planet 9 cluster. It sits closer in, more orderly, more classical. Yet, some researchers point to finer details in its orbital parameters, the precise shape and tilt of its path, and suggest they might still be consistent with a history of gentle nudges from a distant, massive perturber. It is as if Quaoar is not one of the tightly herded sheep, but a creature from the outer edges of the flock, still feeling the shepherd's presence. This connection, while highly tentative, instantly elevates Quaoar from a curious backwater to a potential key witness in one of astronomy's greatest ongoing detective stories. If Planet 9 exists, its gravity would have sculpted the orbits of countless Kuiper Belt objects over billions of years. Each world whose path we can precisely measure becomes a data point, a celestial breadcrumb leading us backward to the predator's den. By studying Quaoar's exact position, its velocity, and the slight oscillations in its orbit, astronomers can run sophisticated simulations. They can ask, if we place a hypothetical Planet 9 here with this mass and this orbit, would it produce a Kuiper Belt that includes an object exactly like Quaoar? In this grand cosmic simulation, Quaoar becomes a test particle, a single dot used to validate or refute the existence of a solar system we have never seen. The implications are staggering. A confirmed link would mean Quaoar's present-day calm is an illusion, its path forever shaped by the invisible pull of a hidden master. It would no longer be just an orphaned world, but a bound servant to a distant, unseen king. Its orderly orbit would then be a product not of a quiet local history, but of a grand, galaxy-spanning gravitational architecture we are only beginning to perceive. This places Quaoar at the heart of a profound question. Are we missing a major planet in our own cosmic backyard? Every new observation of this distant dwarf planet is not just about understanding one frozen world. It is about calibrating the scale of our own ignorance and perhaps finding the map that leads to a discovery that would rewrite every textbook forever. Its potential link to a hidden planet is a future mystery, but one of Quaoar's most present and visible silences is its lack of a tail. This is the coma conundrum. Many icy bodies in the outer solar system, when they swing closer to the Sun, begin to warm. Their surface ices, like frozen carbon dioxide or methane, sublimate, turning directly from solid to gas. This escaping gas drags dust with it, creating a hazy, glowing cloud around the nucleus called a coma, and often the iconic streaming tail that makes a comet so recognizable. Quaoar, however, remains stubbornly inert. Even at its closest approach to the Sun, its perihelion, it shows no sign of a coma, no hint of a tail. It is a frozen stone, silent and dark against the starry backdrop, while other distant objects like the active Centaur's icy bodies orbiting between Jupiter and Neptune put on spectacular shows of outgassing and dust. Why does Quaoar refuse to become a comet? The first and most likely answer lies in its skin. Quaoar may have developed a thick, durable crust. Imagine a lake that freezes over during a long, bitter winter. The surface forms a solid, insulating layer of ice, while liquid water may still remain trapped below. Over billions of years, relentless radiation from space could have processed Quaoar's topmost layers of methane and water ice, baking them into a tough, porous, and dark material akin to a cosmic charcoal crust. This crust acts as a perfect insulator, sealing the more volatile ices beneath it. The weak sunlight at that immense distance simply cannot penetrate deeply enough or provide sufficient energy to break through this armored shell and trigger sublimation. The volatiles are there, but they are locked in a frozen vault. Another possibility is simpler and more final: depletion. Perhaps Quaoar has already spent its volatile budget. In its distant past, during earlier orbital cycles, it may have been more active. Each time it approached the Sun, even this far out, it could have lost a layer of its icy veneer to space. After billions of years of this slow, cyclic erosion, the readily accessible ices near the surface may have been completely exhausted. What remains today could be a desiccated, inert shell over a still volatile interior, with no easy pathway for the remaining gases to escape. The surface we see is a spent fuel tank, but there is a more fundamental idea to consider, one that challenges our assumptions about ice itself. At the temperatures reigning in Quaoar's realm, only a few dozen degrees above absolute zero, the very physics of sublimation may change. The process might be so incredibly slow, so inefficient, that any gas produced immediately refreezes in the microenvironment just above the surface, creating a perpetual, invisible frost cycle that never builds into a detectable coma. The ice isn't inert, it's trapped in a state of eternal, frozen hesitation. This lack of a coma is not an absence of mystery, but a presence of constraint. It tells us that possessing the ingredients for activity is not enough. You need the right conditions, the right surface, and the right internal plumbing to set that activity free. Quaoar's silent face suggests a world that is either expertly insulated, utterly spent, or operating by a rulebook for ice written at the very edge of thermodynamic possibility. The silent, inert surface of Quaoar may hide a subtle rhythm, a slow dance of frost between its poles. While it lacks a dramatic coma, there is intriguing evidence that this world might still experience seasons expressed through possible polar caps. On other icy bodies like Pluto or Mars, we see bright, reflective deposits of frozen volatiles at the poles that grow and recede with the changing solar angle over long orbital cycles. Could Quaoar, in its own slow-motion way, do the same? The idea hinges on a process called seasonal volatile migration. Even at its immense distance, the Sun provides a faint whisper of heat. Over the course of Quaoar's nearly 300 Earth-year orbit, one hemisphere will be tilted slightly more toward the Sun for a long, slow summer, while the other experiences a deep, protracted winter. During the winter, temperatures in the permanent shadow of a polar region could plunge low enough to trap any wandering atmospheric gases, causing them to freeze directly onto the surface as a bright, fresh frost. This would create a temporary polar cap. Then, as that pole swings into the faint sunlight of its summer decades or centuries later, the frost sublimates, migrating back across the surface to refreeze at the opposite, now winter pole. It is a global, millennial-scale sigh of frost, moving from one end of the world to the other. Detecting such caps on Quaoar is a monumental challenge, but astronomers look for subtle asymmetries in its brightness as it rotates. If one pole is significantly brighter and more reflective than the equatorial regions, it could signal a coating of clean, fresh ice. The composition of these hypothetical caps would be a direct readout of Quaoar's atmospheric chemistry. Would they be made of brilliant white nitrogen ice like on Pluto, or darker, reddish methane frost tinted by tholins? Each substance freezes at a different temperature, so the dominant ice reveals the precise chill of Quaoar's winter poles. Even more telling would be asymmetry. If one polar cap is noticeably larger or brighter than the other, it would be a frozen record of climate imbalance. Perhaps Quaoar's orbit is just elliptical enough that one pole experiences a colder, longer winter than its counterpart, allowing more frost to accumulate. Or maybe geological features, like a large impact basin at one pole, create a cold trap that preferentially collects and holds volatiles for millennia. The presence of stable, long-lived polar caps would transform our view of Quaoar from a static ball of ice into a world with a climate, albeit one that changes over timescales longer than human civilization. Their stability is the final question. A cap that persists for only a fraction of Quaoar's orbital year speaks of a thin, active layer of frost in constant motion. But a permanent cap, one that never fully sublimates away, would be a landmark of profound cold. It would indicate a region so perpetually frigid, so deep in shadow or so perfectly composed that it acts as a permanent cold sink, a freezer within a freezer, locking away a portion of the world's volatile budget forever. These faint, theoretical patches of frost are more than just decoration. They are a climate ledger recording the balance between feeble sunlight and the endless cold of space over epochs. Finding them would mean Quaoar, for all its silence, still whispers with the slow, rhythmic breath of the seasons. The silent whisper of frost across Quaoar's poles is one kind of motion, but another, far more energetic force might be at play in its space. The hard vacuum around this dwarf planet is not truly empty. It is a stage for a microscopic drama of electric charge. This is the mystery of charged dust, a hidden force that could hold the key to the impossible ring's survival. On airless worlds, something strange happens to the finest dust grains. They don't just lie there. The sun, even from its incredible distance, bathes Quaoar in ultraviolet light and a thin stream of charged particles called the solar wind. When these energetic photons and particles strike the surface, they can knock electrons loose from atoms in the dust. A tiny grain of ice or silicate, smaller than the width of a human hair, can suddenly become electrically charged, gaining a net positive or negative charge. On a world with no atmosphere to dampen the effect, this charge is powerful. Positively charged dust grains repel each other with surprising force. They can even be levitated, literally lifted off the surface by electrostatic repulsion, launching into a slow-motion ballet above the ground. This phenomenon, called electrostatic lofting, is thought to create the faint, temporary dust halos seen around some asteroids and our own moon. For Quaoar, this process offers a tantalizing possibility, a secret pipeline to its ring. Imagine a constant, invisible rain of these microscopic, charged particles rising from the dwarf planet's surface. Once aloft, they could be caught in Quaoar's gravitational pull and swept into orbit. Over time, this steady trickle of electrostatically launched dust could act as a replenishment system for the ring, feeding it with fresh material to replace any particles lost to collisions or dispersal. It would be a self-sustaining cycle where surface erosion by sunlight itself supplies the ring with new actors. But the role of charged dust may be even more fundamental. It could be the ring's architect. The particles within the ring itself are undoubtedly charged. In that hard vacuum, they are all subject to the same radiation environment. If they carry similar charges, they would repel each other electromagnetically. This electrostatic repulsion could be the very force preventing the ring's particles from coalescing into a moon. Every time gravity tries to pull two specks together, their mutual negative charge might push them apart, like trying to force together the same poles of two powerful magnets. This constant microscopic pushing could maintain the ring in a state of arrested development, perfectly balancing the relentless pull of gravity. It introduces a microphysical mystery into a system we usually describe with orbital mechanics alone. The stability of Quaoar's ring might not be governed solely by the grand dance of gravity from Weywot or hidden moons, but by the invisible, crackling force fields clinging to each individual speck of ice. This shifts our perspective from the cosmic to the quantum, where the fate of a vast celestial structure could hinge on the behavior of subatomic particles on a grain of dust. It suggests the space around Quaoar is not a placid void, but a dynamic plasma environment, a realm where sunlight doesn't just illuminate, it electrifies. Solving this mystery requires us to think in multiple scales at once, from the orbit of a dwarf planet down to the electric field around a single, floating mote of ice. If true, it means Quaoar's greatest secret is written not just in gravity, but in lightning. The invisible crackle of charged dust may shape its ring, but the grandest force governing Quaoar's destiny is the silent pull of a giant. To understand its place in the solar system, we must examine its orbital dance with Neptune, the solar system's gravitational gatekeeper of the Kuiper Belt. This is the resonant tango, a celestial rhythm that can mean eternal protection or eventual exile. Pluto, for example, is locked in a stable 3-to-2 mean motion resonance with Neptune. For every 3 orbits Neptune completes around the Sun, Pluto goes around exactly twice. This gravitational lockstep keeps their paths synchronized, ensuring they never get too close, preventing a catastrophic collision or a disruptive gravitational kick. The question is, does Quaoar share this kind of protected relationship? The answer is nuanced and reveals a far more precarious history. Detailed orbital analyses show that Quaoar is not neatly trapped in a strong, clean resonance like Pluto. Its orbit does, however, show hints of being near resonances, brushing up against these gravitational harmonies without being firmly captured by them. Think of it as a dancer who occasionally falls into step with a powerful partner for a few measures, only to drift out of rhythm again. This suggests Quaoar's relationship with Neptune is one of temporary liaisons and near misses, not a permanent, binding contract. This dynamical detail is a profound clue to its past. If Quaoar were in a stable resonance, it would indicate it has been peacefully coexisting with Neptune for the age of the solar system, a local object that was gently shepherded into its current orbit during the planet's early migration. Its flat, orderly path would be the signature of this gentle history, but its lack of a firm resonance tells a different, more turbulent story. It implies Quaoar may have experienced a far more chaotic journey. It could have been scattered by Neptune's gravity in the distant past, bouncing through different orbital zones, sometimes feeling the giant's rhythmic pull, sometimes escaping it. This chaotic past aligns with the idea of Quaoar being an immigrant from the inner solar system, violently ejected and only later finding a semblance of stability. Its current orbit, while orderly, may not be its final resting place. The lack of a strong resonance means it lacks Neptune's permanent gravitational guarantee. Over billions of years, subtle perturbations from other giant planets or passing stars could slowly alter its path. It might eventually be nudged into a true resonance, finding a permanent safe harbor. Or it could be destabilized, its path becoming more elliptical and tilted, eventually being flung inward toward the giant planets or outward into the scattered disk, or even ejected from the solar system entirely. Quaoar's future is not written. Its orbital relationship with Neptune is that of a cautious neighbor, not a bound vassal. This tango is one of cautious steps and uncertain turns, a dance where the music could change at any moment, rewriting the destiny of this frozen world in an instant. This ghostly map of light and shadow reveals a world of stark contrasts. From the subtle flickers in its reflected light, astronomers can begin to sketch a hypothetical albedo map of Quaoar, a chart of its bright and dark territories. This is not a photograph, but a portrait painted by mathematics, revealing a surface that is anything but uniform. Vast, dark expanses likely stretch across its face, regions where ancient, radiation-baked tholins coat the ice in a layer of complex organic tar. These are the old continents of Quaoar, places that have stared into the void for billions of years, their colors deepening under an endless rain of cosmic rays. But interrupting these dark plains are brilliant, reflective patches. These could be the scars of youth, impact basins where a relatively recent collision blasted away the dark upper layer, exposing a subsurface stratum of pristine, bright water ice. Imagine a cosmic hammer strike punching through a dark, dusty crust to reveal the gleaming white material beneath, a fresh wound that has not yet had time to darken. Alternatively, these bright regions could be the frozen flows of cryovolcanic activity, a slushy eruption of water, ammonia, and methane from a subsurface ocean would spread across the landscape like a slow-moving glacier before freezing into a smooth, highly reflective plain, effectively repaving an ancient, cratered terrain with a brand new sheet of ice. The map might also show gradients, areas where dark and bright materials have been mixed and churned by lesser impacts or geological slumping, creating a mottled, intermediate terrain. Each contrast on this inferred map is a sentence in a geological story. A sharp boundary between dark and bright suggests a sudden, catastrophic event like an impact or a focused eruption. A more gradual, blended edge might speak of slower processes, like the steady sifting of dark dust across bright ice over eons of micrometeorite gardening. The very pattern of these regions holds clues. Are the dark areas concentrated in one hemisphere, perhaps the one that has faced the direction of travel for millions of years, collecting more interstellar dust? Are bright patches clustered near potential cryovolcanic hotspots, like the bases of towering ice mountains or the rims of fissures? This patchwork quilt of albedo is a forensic record. It tells us that Quaoar's history is not one of quiet, uniform decay, but a dynamic saga of violence from above and upheaval from within. The dark regions whisper of unimaginable age, while the bright spots shout of moments, perhaps recent on a geological scale, when the world was still alive enough to change its own face. Amidst the faint flickers of its light curve and the ghostly whispers of its gravitational field, another secret may be orbiting in the dark. Some datasets contain subtle anomalies, gravitational nudges that cannot be fully explained by Quaoar's known moon, Weywot, alone. This has led to a compelling speculation, the possibility of a second moon. Imagine a tiny, dark companion, perhaps only a few kilometers across, tracing a silent path around the dwarf planet. It would be a ghost in the machine, its presence inferred not by direct sight, but by the slight, unexplained wobbles it imparts on the system. Finding such an object would be like hearing a faint, second heartbeat in a room you thought held only one person. The challenge of detection is immense. A small, dark moon could easily be lost in the overwhelming glare of Quaoar itself when viewed from Earth, a speck of charcoal hiding next to a distant spotlight. Even more intriguing is the possibility that this moonlet might not be orbiting in clear space at all. It could be embedded within the mysterious ring itself, acting as a gravitational anchor or a shepherd. In this scenario, the moon would be cloaked by the very structure it helps maintain, its faint form blurred into the collective glow of countless icy particles. We would be searching for a single tree hidden deep within a vast circular forest. The gravitational role of such a hidden moon would be profound. It could be the missing piece in the puzzle of the impossible ring. A small shepherd moon, orbiting just inside or outside the dense band, could provide the precise gravitational nudges needed to keep the ring particles confined, preventing them from either spreading out or clumping together. This unseen shepherd would be the active guardian, the celestial traffic cop maintaining order in a zone where physics says chaos should reign. Its gentle, persistent tugs could explain the ring's coherence far outside the Roche limit, offering a classical solution to a deeply unclassical problem. Alternatively, a second moon could be the key to understanding Weywot's wildly tilted orbit. The gravitational dance between two moons around a central planet is a complex and often unstable ballet. A small, previously undetected companion could have been locked in a gravitational resonance with Weywot for billions of years. Their mutual interactions could have slowly, over eons, pumped energy into Weywot's orbit, gradually lifting it from an equatorial plane to the severe inclination we see today. This would mean Weywot's odd path is not solely the product of a single ancient impact, but the result of a long, slow gravitational conversation with a sibling that we have only just begun to suspect. The discovery of a second moon would instantly transform Quaoar from a binary system into a miniature planetary family. It would add a new variable to every gravitational equation, forcing us to re-simulate the system's history and future with this additional actor in play. The potential for complex resonances and subtle perturbations grows exponentially, painting a portrait of a far more dynamic and crowded celestial neighborhood. It suggests that Quaoar's gravitational influence extends further and commands more loyalty than we ever imagined, with not one, but possibly multiple attendants caught in its frozen grasp. The hunt for this phantom moon continues, a search for a shadow that could illuminate everything. The search for hidden moons leads us to the most profound question of all: what is Quaoar in the grand story of our solar system? Beyond the rings and the red stains and the tilted moon, a radical theory is emerging, one that elevates this frozen world from a curious dwarf planet to something far more significant. Quaoar may be a planetary embryo, a failed protoplanet frozen in time. This is not just a label, it is a revelation about its very nature and its place in cosmic history. In the earliest days of our solar system, the disk of gas and dust around the young sun was a construction zone. Dust grains collided and stuck together, forming pebbles, then rocks, then mountain-sized planetesimals. The largest of these planetesimals, through countless collisions and gravitational captures, grew into the cores of the planets we know today, but not all of them made it. Some were left behind, their growth stunted, frozen in an intermediate state between a simple ball of rubble and a true planet. These are the planetary embryos, the almost worlds. Quaoar, with its specific characteristics, fits this ancient blueprint perfectly. Its size is the first clue. At roughly 1,100 kilometers in diameter, it is large enough to have undergone significant internal processing, but not so large that it swept up all the material in its orbital neighborhood. It is a Goldilocks object, big enough to be complex but small enough to have been stranded. Its astonishingly high density is the second, and perhaps most compelling, piece of evidence. A fluffy snowball from the outer solar system should not be so heavy. That dense, rocky core speaks of differentiation, the process where heavier materials like rock and metal sink to the center of a forming body, while lighter ices rise to the surface. This is not the behavior of a simple pile of icy debris. It is the signature of a body that grew massive enough and was warm enough in its youth to partially melt and separate into layers. It was on its way to becoming a miniature terrestrial planet, a rocky world with an icy mantle. Its composition, with water ice, methane, and complex organics, represents the primordial ingredients available in its specific construction zone. It is a snapshot of the chemical conditions in that part of the protoplanetary disk over 4 billion years ago. If this theory is true, then Quaoar is not merely an object in the Kuiper Belt, it is a time capsule. It is a fossil from the era of planetary birth, a preserved example of what the building blocks of Uranus and Neptune might have looked like before they grew into giants. Studying Quaoar is not just studying a distant world, it is conducting an archaeological dig into the solar system's deepest past. We are looking at a blueprint that was never fully realized, a glimpse of what might have been if the gravitational chaos of the young solar system had played out differently. This perspective changes everything. The ring is no longer just a ring, it could be a relic disk from that embryonic era. The tilted orbit of Weywot is not just an oddity, it could be a record of the violent collisions that were the daily reality of that formative time. Every mystery we have explored becomes a clue in a larger investigation, the investigation of how planets are born. Quaoar stands as a silent monument to that unfinished work, a planetary embryo that never grew up, offering us a direct, untouched sample of the solar system's infancy. That frozen blueprint of planetary birth holds one final, dynamic secret, the ultimate fate of its impossible ring. We have marveled at its defiance of gravity, but nothing in the cosmos is permanent. What destiny awaits this delicate band of ice? Will it fulfill the gravitational command it currently resists and coalesce into a new moon, or will it meet a different, more ephemeral end? The answer depends on a silent war between competing forces, a battle whose outcome will unfold over timescales that stretch human imagination, yet may offer us a front-row seat to a cosmic birth. The most natural fate, the one dictated by textbook physics, is moon formation. Outside the Roche limit, the particles in the ring should feel a gentle, mutual attraction. Over millions of years, these tiny specks of ice should collide at slow speeds, stick together, and gradually build larger and larger clumps, a process called accretion. This is how we believe most moons formed around planets. If this process begins, we could witness the slow-motion assembly of a new world, a second moon for Quaoar born from the very ring that now encircles it. This new moon would likely be small, perhaps only a few kilometers across, and its orbit would be dictated by the ring's current location, far from Quaoar's surface. It would be a direct test of our models of satellite formation, happening almost in real time on a cosmic scale. But the ring's continued existence suggests powerful forces are fighting this outcome. The persistent electrostatic repulsion between charged particles, or the gravitational shepherding from unseen moonlets, might be strong enough to prevent those gentle, sticky collisions forever. If these anti-coalescence forces win, the ring's fate is dispersion. The constant, subtle nudges from solar radiation pressure, the gravitational perturbations of passing stars over eons, and microscopic collisions between the particles themselves could very slowly spread the ring out. Its density would decrease, the band would widen and fade, and eventually the particles would drift apart, becoming just another diffuse cloud of dust in the Kuiper Belt, losing their coherent, beautiful structure to the entropy of deep space. There is a third, more dramatic possibility: reaccretion. The ring particles do not orbit in a perfect vacuum. They are subject to drag from the tenuous interplanetary medium and the subtle but persistent influence of Quaoar's own gravity. This could cause their orbits to decay, very slowly spiraling inward over hundreds of millions of years. If this happens, the ring would rain down onto Quaoar's surface in a perpetual, microscopic meteor shower. This silent snowfall of primordial material would coat the dwarf planet's ancient ice with fresh frost, potentially replenishing its surface volatiles and subtly altering its albedo over geological epochs. The ring would not form a new moon in the sky, but would instead return to the world from which it may have originally come, completing a cosmic cycle. The timescales for any of these outcomes are astronomically long, likely spanning tens to hundreds of millions of years. We will not see the conclusion in our lifetime or in the lifetime of our species. Yet herein lies the breathtaking opportunity. For the first time, we have identified a structure caught in the act of deciding its own future. By monitoring Quaoar's ring over the coming decades and centuries with ever more powerful telescopes, we might see the earliest stages of this process. We could detect the first signs of clumping within the ring, the initial aggregation of particles into moonlets, or we might measure a gradual widening, the first hint of dispersion. This is like finding a single frame from a movie that lasts 1 billion years, and now we have the chance to watch the next few frames play out. It is a rare and precious chance to observe moon formation or ring dynamics in what amounts to real time, a process usually consigned to the distant past. The ultimate fate of Quaoar's ring is more than a prediction, it is a promise written in ice. Whether it builds a new world, fades into dust, or returns home, its journey will teach us the final chapter in the story of how celestial structures live and die. This enigmatic ring is not just a mystery to be solved, but a clock we have just begun to read, ticking away in the silent dark, counting down to a celestial transformation we are privileged to witness from the very beginning. Quaoar stands as a crown jewel of the Kuiper Belt, a single frozen world containing 25 profound mysteries that challenge our every assumption. From its impossible ring defying the Roche limit to its dense, rocky heart in a realm of ice, each puzzle forces us to rewrite the textbooks. Its surface is a contradiction of ancient craters and a mysterious red stain, while its moon Weywot circles on a tilted path screaming of ancient violence. We detect hidden warmth hinting at a subsurface ocean, yet search in vain for a wisp of atmosphere. Its light flickers irregularly, its orbit is suspiciously orderly, and its very shape is caught between a sphere and a splat. The chemical signatures on its surface are unidentified. Its relationship with Neptune is a precarious dance, and it may hold the gravitational fingerprints of a hidden planet 9. It is a potential planetary embryo, a failed protoplanet frozen in time, surrounded by charged dust and possibly even hidden moons. This world is not one mystery, but a symphony of them, a cosmic puzzle box where every solved question only reveals 3 more. Each unanswered riddle, from the fate of its ring to the source of its internal heat, is a direct challenge to our models of how solar systems form and evolve. This is why Quaoar is no longer just a distant speck. It is a beacon for the next generation of exploration. Proposed missions equipped with powerful new telescopes and perhaps even dedicated probes are being designed with this dwarf planet in their sights. They aim to map its surface in detail, to sniff for traces of an exosphere, and to finally determine if it truly is a binary world. The ongoing exploration of our solar system's final frontier is alive with discovery, and Quaoar sits at the heart of it, a reminder that the greatest secrets are often hidden in plain sight, waiting for a curious mind to look. Which of its 25 mysteries fascinates you the most? Share your thoughts and never stop looking up at the stars, for the next great revelation is always just over the horizon.